Now we will discuss about oxoacids of phosphorus. Phosphorus forms number of oxoacids in which it shows different structures and different properties. The first oxoacids of phosphorus is hypophosphorus acid. Hypophosphorus acid. The chemical formula of hypophosphorus acid is H3PO2. Now we draw the structures. Phosphorus is the central element. You make the OH pair. How many OH pair are possible? 2 OH pairs. Attach these OH pair to the central element. Okay. Now we are left with one hydrogen. We also attach this hydrogen to the central element. Okay. Keep in mind phosphorus has 5 valence electron. So it must form 5 bonds. You can see it is forming only 3 bonds, means its valency is not satisfied. I remove this oxygen, attach this oxygen to phosphorus via double bond. Now you can see the valency of phosphorus is satisfied. This is the structure of hypophosphorus acid. Now we can calculate the oxidation state. This is oxide, this is hydroxyl group -1, hydrogen attached to non-metal shows +1 oxidation state, and it is also +1 oxidation state. -1 +1 will cancel out. Phosphorus -2 + 1, -2 and +1 is equal to 0. Phosphorus -1 is equal to 0, and phosphorus is equal to +1. Okay, in this oxoacids, phosphorus is present in +1 oxidation state. Let me write the oxidation state. Oxidation state. It is +1. Okay, now next we have basicity. Basicity is the number of hydrogen attached directly to oxygen. In oxoacids. Okay, now you can see how many OH group are present. Only one OH is present. Okay, hydrogen attached to oxygen. Okay, in oxoacids represents the basicity. Okay, only one OH is there in which hydrogen attached to oxygen. These 2 hydrogens are attached to phosphorus. Okay, so these 2 hydrogen will not contribute to the basicity of this acid. Why? Because, pay attention very carefully, the removal of this hydrogen is quite easier, because if I remove this hydrogen, this oxygen will bear negative charge, and this negative charge will be the part of resonance, because double bond, single bond and negative charge. Removal of this hydrogen will result in the stability of this acid. Okay, but if I remove these 2 hydrogens, immediately charge will come over here, and double bond, immediately charge is there, it will move towards instability. Okay, it will become unstable. That's why you don't want to be unstable. Removal of these hydrogens will not contribute to the basicity of this acid. Okay, that's why it is only resulting in, it is only counted, when we talk about the basicity of this acid. So basicity is the number of hydrogen attached directly to oxygen in oxoacids, because these hydrogens can be removed very easily. So basicity, you can see only one is there, basicity. So I can write, it is monobasic by nature. This acid is monobasic by nature, means only one OH group is present in which hydrogen can be removed. Now we talk about the preparation reaction. Okay, preparation reaction. We have the phosphorus. When phosphorus reacts with water, okay, even small quantity, you can see phosphorus can react with the moisture present in air. It is very fast reaction. Okay, water, it reacts with water, and when this reaction is quite fast, so if the possibility of forming gases are there, these gases will escape immediately. Like we have phosphine gas immediately will escape. This is phosphine gas, and remaining portion will get, that is hypophosphorus acid, that is H3PO2. Now we can balance this equation. 4 phosphorus, 1 phosphorus multiplied by 3. Phosphorus is balanced. How many hydrogen? 3 3 are 9, 3 12 multiplied by 6. Okay, equation is balanced. By using this method, we can prepare this oxophosphorus acid. Okay, now let's move on to the next oxoacids of phosphorus. Next we have orthophosphorus acid. The chemical formula is H3PO3. We draw the structure. Phosphorus is the central element. How many OH pair are there? 3 OH pair are present. We attach these OH pair to the central element. Okay, we need to satisfy the valency of phosphorus. I remove this oxygen, attached to this phosphorus through double bond. Now we can see this is the structure. Okay, valency of phosphorus is satisfied. Now we calculate the oxidation state. Hydroxyl group -1 charge, hydroxyl group -1 charge, hydrogen attached to non-metal +1 charge, and this is oxide -2. Okay, +1 -1 will cancel out. Then we have phosphorus -2 and -1 is equal to 0. Phosphorus, and it is -3 is equal to 0. Phosphorus is present in +3 oxidation state. In this oxoacids of phosphorus, oxidation state is +3. Now we calculate basicity. Basicity is the number of hydrogen attached directly to oxygen in oxoacids. So how many OH are there? There are 2 OH in which hydrogen attached to oxygen. Okay, then basicity can be 2, and we can write basicity is dibasic. Di means 2, dibasic. Di means 2 hydroxyl group are present in this acid. Now we talk about the preparation reaction. Okay, now we talk about the preparation reaction. Orthophosphorus acid can be prepared by the hydrolysis of tetraphosphorus hexaoxide. Okay, we add water molecule. Directly we get H3PO3. Okay, H3PO3. Now we can balance this equation. 4 phosphorus multiplied by 4. How many hydrogen? 4 3 are 12 multiplied by 6. Equation is balanced. This is one method. Okay. Second preparation reaction we have already learned in the trihalides of phosphorus. PCl3 reacts with water. Okay, this is a double displacement reaction. It will give us P3 plus and it is 3Cl minus ion. It will give us H plus ion and this is OH minus ion. Okay, H plus ion will combine with Cl minus ions. I take 3 molecules of water, then you can see that is how combination will be taking place. Pass to negative attraction will be there. Then we get a 3 Cl and then we have P attaching with 3 hydroxyl group, POH whole thrice, or it can also be written as H3 and PO3. Okay, orthophosphorus acid. Orthophosphorus acid, or it can also be called as phosphorus acid. Only phosphorus acid, that is also correct. Okay, these are the 2 methods we have for the preparation of orthophosphorus acid. Now next method is also there. Next method we have H3PO2. Okay, before this we learned about H3PO2. Okay, on heating it undergoes disproportionate reaction. Disproportionate, pay attention here. 2 to 4, it is present in +1 oxidation state. Phosphorus present in its intermediate oxidation state undergoes disproportionate redox reaction. Okay, so it converts into H3PO3 and releases. On heating is being done, that's why gas will escape. Phosphine gas is there. In this case 3 2 6, it is present in +3 oxidation state. It is present in -3 oxidation state. +1 to +3 oxidation, +1 to -3 reduction. Okay, so it is a disproportionate redox reaction. Okay, now you can balance it. We have multiplied by 3 and multiplied by 2. 2 3 6, 9. 3 3 9. Okay, equation is balanced. So this is the third preparation reaction for the orthophosphorus acid. Now let's move on to the next oxoacids. Next we have orthophosphoric acid. It can also be called as phosphoric acid. Chemical formula is H3PO4. P is the central element. Draw the structure. How many OH pair are possible? 3 OH. Attach these OH directly to the central element. Still one oxygen is left. We can satisfy the valency of phosphorus by attaching to phosphorus. This is the structure we have. Simple. Now we can calculate the oxidation state. Oxide, hydroxyl group, and hydroxyl group. Okay. -2, -3, -4, -5. Phosphorus. -5 is equal to 0, is equal to +5. Okay. You can see in this oxoacids, phosphorus is present in its highest oxidation state. Means it acts as a strong oxidizing agent because it will always undergo reduction reaction in any chemical reaction. We got oxidation state, that is +5. Now we talk about basicity. Number of hydroxyl group present 3, 1 2 3. It can release 3 hydrogen, 1 hydrogen, 2 hydrogen and 3 hydrogen. Okay, Once it releases 3 hydrogen, it will be in highly stable state. Why? Because too much resonance will be there. Negative, negative, negative. Resonance, resonance, resonance. Okay. Basicity. Since it has 3 hydroxyl group, we can say it is tri-basic by nature. It is tri-basic by nature. Now we talk about preparation reaction. You might have learned about phosphorus pentoxide, okay, diphosphorus pentoxide, okay, and it is present in P4O10 form because P2O5 undergoes dimerization, converts into P4O10 to be in stable state. Okay, we have P4O10 undergoes hydrolysis, reacts with water. Okay, too much water will not be there, very little bit quantity of water. Keep in mind, it acts as a dehydrating agent. Whatever the quantity of water is there, it will absorb. Okay, it acts as a better dehydrating agent. Combination reaction will be there because it will absorb water molecule. So it forms as 3 and it is PO4. 4 phosphorus multiplied by 4. How many hydrogen? 4th is a 12 multiplied by 6. Okay. Now we can see if oxygen are balanced. 4 4 is 16, 6 plus 10 is equal to 16. Okay, equation is balanced. Now next, we had orthophosphorus acid as 3 and it is PO3. It also undergoes disproportionate redox reaction. In general, the phosphorus present in +3 oxidation state easily undergoes disproportionate redox reaction and converts into 2 substances. One is in its highest oxidation state, another in its lowest oxidation state. Okay, we get as 3PO4 and then we have PH3. It is lowest oxidation state. 4 2 is 8 and here we have +5 oxidation state. Okay, +3 to +5 oxidation, +3 to -3 reduction. Disproportionate redox reaction, same element is undergoing both oxidation and reduction reaction. We can balance this equation. Multiplied by 3, we can have 4 and it is 3. Okay, 3 phosphorus plus 1 phosphorus is equal to 4 phosphorus. 4th is a 12, 3 3 is a 9, 3 12. Okay, 4th is a 12, 4th is a 12. Oxygen is also balanced. Okay, one more reaction you might have learned in the chemical reaction of nitric acid. Nitric acid is a strong oxidizing agent. Okay, and in case of nitric acid, we had learned, nitric acid oxidizes phosphorus into its highest oxidation state into H3PO4. Okay, you can see this chemical reaction is given there in nitric acid. Okay, so by using this method also we can prepare phosphoric acid, orthophosphoric acid or phosphoric acid, both are same. Okay, so these are the 3 preparation reaction, first, second and third. Okay, now let's move on to the next oxoacids. Next we have pyrophosphorus acid. And the chemical formula is H4P2O5. 2 phosphorus are there. Okay, 2 phosphorus and odd number of oxygen is there. Odd number of oxygen, then phosphorus, oxygen, phosphorus linkage will be there. POP, we say POP linkage is present in this acid. Now draw the structure. P, O and P. Okay, how many OH pair are possible? 2 OH pair are possible. 2 OH. I attach OH pairs to each phosphorus. Okay, still 2 oxygen are left. Attach each oxygen to each individual phosphorus. We are left with 2 hydrogen. You can see each phosphorus is forming how many bond? 4 bond. I do one thing, I take hydrogen and take hydrogen. Okay, now we can see valency of phosphorus is satisfied. It is forming 5 bond. 2 plus 2 and plus 1 is equal to 5. Okay, this is the structure we have. Now we calculate the oxidation state. If you look at here, each phosphorus is in the same environment. That's why the oxidation state of each phosphorus will be same. Okay, oxygen, it is -2, it is hydroxyl group, it is -1, it is present in +1 oxidation state. You can see this is oxide. Okay, it is showing -2 oxidation state. Since it is connected to 2 phosphorus, that's why its oxidation state will divide. minus 1 will go to this side, minus 1 will go to this side. Okay, then plus 1 minus 1 will cancel out, and then phosphorus minus 2 and this is minus 1 is equal to 0. Phosphorus is present in plus 3 oxidation state. Each phosphorus minus 2 minus 1, because this is going to get cancelled, plus minus will cancel out, minus 2 minus 1 plus 3 oxidation state, minus 2 minus 1 plus 3 oxidation state. The oxidation state of each phosphorus is plus 3, so we can say plus 3 is there. Okay, sorry, we can say in the sense of, I am talking about basicity. Okay, now we talk about basicity. It's very clear how many hydroxyl group are present. Hydrogen attached to oxygen, 1 2 hydroxyl group are present. That's why it is dibasic by nature. We talk about basicity, it can liberate how many hydrogen? 2 hydrogen. It is dibasic by nature. Dibasic by nature. Now we talk about preparation reaction. Okay, preparation reaction. Preparation reaction, we have phosphorus trichloride reacting with phosphorus acid, that is H3 and it is PO3. Okay, you might have learned the chemical reaction of phosphorus trichloride. It can release 3 chlorine, because it is a very good chlorinating agent. Okay, releases 3 Cl. Okay, and it takes 3 hydrogen from here, forming 3 HCl. Okay, and so remaining portion will go to H4P2O5. This is the chemical reaction we have. This is the chemical reaction. Remaining we get as a main product H4P2O5, that is pyrophosphorus acid. Now we can balance this equation. Okay, balance this equation. Cl is balanced. I multiplied by 5 and I take it is 3. 3 2 is 6 and 5 plus 1 is equal to 6. Phosphorus is balanced. What about hydrogen? 4 3 is 12 plus 3 15 and 5 3 is 15. Hydrogen is also balanced. Okay, this is the method we use to prepare pyrophosphorus acid. Okay, now let's move on to the next oxoacids. Next we have hypophosphoric acid. Chemical formula is H4P2O6. Even number of oxygen are given there. 2 phosphorus are there. That's why phosphorus linkage will be there. Okay, phosphorus and phosphorus. How many OH pair are possible? 4 OH pair are possible. Okay, I connect these phosphorus and so I divide these OH pairs. OH pair, OH pairs, OH pair, OH pairs. I attach 2 OH pair to each phosphorus. Okay, now still 2 oxygen are left. You know, I can attach each oxygen to individual phosphorus to satisfy the valency. You can see each phosphorus is forming 5 bond. Valency is satisfied. Okay, this is the structure we have. Now calculate the oxidation state. Okay, there is no electronegativity difference. That's why there is no pulling off, gaining of electron. It is minus 2. It is what? Minus 1. It is minus 1. Minus 2 minus 1 minus 1. Total plus 4. Phosphorus will show plus 4 oxidation state, because it is going to be P minus 2 minus 1 is equal to 0, then is equal to plus 4. Both each phosphorus are in the same environment. That's why they will show same oxidation state. Okay, oxidation state we got for each phosphorus, that is plus 4. Now we have basicity. It's very clear. Each phosphorus is having 2 hydroxyl group. Total number of hydroxyl group are 4. Then basicity is going to be tetrabasic, 4. Basicity, tetra means 4. Tetrabasic by nature. It can release 4 hydrogen. Okay, to be in unstable state. Okay, 4 hydrogen, 1 2 3 4. Now we talk about the preparation reaction. Okay, it reacts with it does not react with. Okay, red phosphorus reacts with. Okay, red phosphorus P4, allotrope of phosphorus. Okay, it is less reactive than white phosphorus. Okay, sodium hypochlorite NaOCl. Keep in mind it is a very good oxidizing agent because it can release oxygen, convert into NaCl. Okay, and we take water molecule also. Okay, so in this case what happens exactly, we get the main product. It is a very good oxidizing agent. How the reaction takes place, you know, NaOCl, and it is NaCl and releases nascent oxygen. Okay, so it is acting as oxidizing agent only. Okay, and it will undergo oxidation. Phosphorus will undergo oxidation, so it will liberate nascent oxygen and convert into NaCl. Let me write NaCl over here, NaCl. Next, remaining will be the main product, that is hypophosphoric acid. We have H4P2 and O6, H4P2O6. Okay, now we can balance this equation. 4 phosphorus multiplied by 2. How many oxygen are there? How many oxygen? We can have 4 to the 8. So I do one thing, hydrogen case 4 oxygen, 6 to the 12 multiplied by 8. Equation is balanced. Okay, equation is balanced. That is, by using this method we can prepare, you know, that is hypophosphoric acid, H4P2O6. It is tetrabasic by nature. Okay, it is tetrabasic by nature. Next is pyrophosphoric acid. Chemical formula is H4P2O7. Odd number of oxygen is there. That's why, you know, POP linkage will be there. POP linkage. We have P and P. POP linkage. How many OH pair are there? 4 OH pair are possible. 4 OH pairs. I attach 2 OH pair to each phosphorus. Okay, each phosphorus. How many oxygen are left? Okay, 1 2 3 4 5. 2 oxygen are left. I attach these oxygen to each phosphorus to satisfy the valency. This is the structure we have. Clear? Each phosphorus is in the same environment. Okay, it is -2, it is also -1, it is also -1. Okay, and this is -2, and it is shared by 2 phosphorus. That's why -1 will go to this phosphorus, -1 will go to this phosphorus. -2, -1, -1, -4 and -5. Okay, the phosphorus will show P -2, and then it is -1, -1, -1 is equal to 0. P minus, what is that? We got -5 is equal to 0 and shows +5 oxidation state. Each phosphorus is in the same environment, that's why it will show +5 oxidation state. Oxidation state of each phosphorus is +5. Now we talk about basicity. Number of hydroxyl group present in this acid. Oxoacids 1 2 3 4, tetrabasic. Okay, basicity is tetrabasic. It can liberate 4 acidic hydrogen. Okay, very good acid. Okay, 4 acidic hydrogen it can liberate. Now we talk about preparation reaction. We have orthophosphoric acid, that is H3PO4. Okay, if we heat it at 300 degrees Celsius, so it will remove water. If water molecule is present, I remove water molecule, and remaining will be the main product, that is H4 and H2O7. Okay, 2 phosphorus multiplied by 2. Okay, that's it. Heating is done, remove water molecule, remaining is the main product. That's it. Pyrophosphoric acid. Okay, sorry I missed this RO. Pyrophosphoric acid, H4P2O7. Now let's move on to the next oxoacids. Next we have metaphosphoric acid. Chemical formula is HPO3 N. N value can be 1 2 3 so on. Okay, it has cyclic structure. If I take N value is 3, then it will become HPO3, and we have 3 is there in place of N. We can say cyclotri, 3 is there, cyclotri metaphosphoric acid, metaphosphoric acid. Okay, odd number of oxygen POP linkage will be there. Cyclic structure is there because cyclo we have added. P, you can write we have P oxygen and P is there. Okay, O and then we have P, O and P. Okay, POP, POP, POP. Okay, 3 phosphorus, 1, 2, 3. In general, I can write as 3P3 and 3 3 9 O9. Okay, that's what chemical formula we get. How many OH pair are possible? 3 OH are attached. 3 OH are present. So we attach 3 OH to each phosphorus. Phosphorus is the central element. How many oxygen we have used? 3 plus 3 is equal to 6. Still 3 oxygen are there. To satisfy the valency of phosphorus, we attach oxygen to each phosphorus. Okay, we attach oxygen to each phosphorus. Structure is ready. Now calculate the oxidation state. This is the structure we have. -2, it is -1, it is -2, but -1 will go this side. It is also -2, -1 will go this side. -2, -1, -1, -1, -5. P -2, -1, -1 is equal to 0. -1, -1, -1 and -2. Then we can see P is equal to +5. Each phosphorus is in the same environment. That's why the oxidation state of each phosphorus will be +5. Okay. And what about basicity? How many hydroxyl group are present? 3. Basicity, tribasic, basicity, tribasic by nature. It depends on the N value. Okay, if N value is 2, it will change. N value is 4, it will change. Basicity. Now we talk about the preparation reaction. We have learned just now in the phosphoric acid is there. Pyro, and that is H4P2O7. H4P2. Okay, H4P2O7 is there. H4P2O7. If we heat, it will liberate water, and remaining portion will be the main product, that is phosphoric acid, metaphosphoric acid, HPO3. Okay, 2 phosphorus multiplied by 2. Okay, 2 hydrogen balance 7. Okay, this is the method we have for the preparation of metaphosphoric acid. Another preparation reaction we have, that is H3PO3. When it reacts with Br2, okay, 2 hydrogen, it can release 2 hydrogen, and 2 Br will combine together to form HBr, and remaining will be the main product, that is HPO3. Okay, HPO3. Because 2 hydrogen gone with Br, so 1 hydrogen is left, HPO3. That's it. This is the first preparation reaction, and this is the second preparation reaction. Keep in mind, out of all the oxoacids of phosphorus, hypophosphorus acid acts as a better reducing agent. Okay, better reducing agent. Keep in mind, phosphorus is present in its intermediate oxidation state. Okay, it reduces silver nitrate into silver. It removes the silver from this compound. +1 and it is 0. You can see it is undergoing reduction. Then it will undergo oxidation. Let me write the reaction. AgNO3, and we have H3PO2. H2 is also there. Converts AgNO3 into Ag, and it produces 2 strong acid, HNO3 as well as H3PO4. In both acids, central element is present in its highest oxidation state. Balance this equation, 4 multiplied by 4. Okay, we have 4 hydrogen plus 3, 7 hydrogen, 3 multiplied by 2. What about oxygen? Okay, silver nitrogen is balanced, nitrogen 4 nitrogen 4 nitrogen balance. Okay, 4 silver 4 silver, equation is balanced. Okay, you can see it is +1 oxidation state, 0 oxidation state. This is what reduction. Okay, in this case 2 to the 4, +1 oxidation state present in highest oxidation state. This is what oxidation. Okay, this is what oxidation, act as a reducing agent.